Our next speaker is our keynote today, and we're very fortunate to have Dr. Dunbar Barney. Dr. Barney received his BS and his PhD degree from MIT and is deeply involved in the solar and electric vehicle innovations at so many levels. He class on solar cell design and processing, integrates patents and innovations with practical engineering knowledge to help students evaluate the new technologies as daily classroom discussion and topics. Professor Barney has been modeling and measuring how solar powered overlaps with the emergency of our electric transportation through the Solar Tube Vehicle Project. Appreciate Dr. Barney taking his time out to join us, and I welcome you to our EV conference.
So it's fun to be working in an advanced technology area, electric vehicles, and my interest actually covers over into solar power and how that might feed electric transportation that is as green as possible. The standard kind of plug-in that we use, level 2 or even DC fast charge, these are hardware that you can buy, and so you think about, well, what are we going to do at the university that would innovate with those things? These are standard, off-the-shelf kind of products, and in fact, we have a lot of ways that we use or misuse things depending on choices that we make about installation locations or the usage patterns. Do we charge for fee for use? Do we allow easy operation? And so what I want to point out are some ways that we're working on campus to use our facility and the installation as a kind of a laboratory for to learn about ways to improve installation and usage. So I call it a living learning laboratory. We have the normal operations going on. We come to class, we teach, we have dining, the dorms, people commute to work, but at the same time, we can measure those things and take data on how things are being used. And so we have data, and we have students who are trying to learn about technologies, and those are ideal candidates to take data and try and process that to learn new things. And eventually those students graduate and they become your future excellent employees. So I'm going to go through some case studies of data that we're collecting and the kinds of interpretation that we're making of it. I'll look at a user ecosystem for a congested parking lot that's sort of standard level 2 workplace charging. I'll give an example also of EV used in a fleet mode and how we can collect data on fleet operations. And then I will end with a kind of a commentary on how solar feeds into the electric vehicle and plug-in. And again, it impacts on what we've learned from user behaviors in our ecosystem. So just to give you a little introduction about where the most data has come from on campus, these are actually there are 4 level 2 chargers over by engineering. This is actually from Google Maps, and you can see, well, one thing you can tell about this parking lot immediately is every spot is full. So this is a congested lot. Even all 4 of the plug-in spots are taken, and so potentially charging those 4 vehicles during the time whenever this satellite went by. Now, what is related to that, okay, this is also from Google Maps. If you go into Street View, you can drag the little man over and you can see this is what they had, and that's, again, the Chevy Volt. So our Parking and Transportation Office has made the choice not to have those spots be EV only. So the signage that we have, it says preferred, but there's no ticketing that happens. So there are times when we have other people, because it's a congested lot, regular gasoline cars will park in those spots. And again, then that paralyzes that spot for as long as someone's parked there. So that's a wasted infrastructure for that period of time. So now, in fact, with 4 spots, that's not very many, actually. We have maybe 10 or 20 different regular commuters into that parking lot who have plug-in vehicles, would like to plug in. And so usually, for the typical kinds of cars that are plugging in these days, Chevy Volts, we have a couple of Teslas and such, but most of the cars, by the time you get to work, you haven't really drained that much of the battery. So by the time you plug in, if you're one of the first people there, you plug in and the battery gets full by lunchtime or something. And so, so what we have done as a group of cooperative users is we've shared email addresses, we have a listserv, and we communicate. And so throughout the day, when someone is moving their car or realizes their car is full, then we're essentially sharing and doubling the use for those 4 charging spots. Now, all 4 of those are monitored with very standard kind of e-gauge data logging, and so we can, and that data is actually online available to the user community. I could give you that link if you were interested. The kind of data that are presented here is an entire day. You can see the total power that's being used for the combined 4 plug-in. And you know, it's no surprise every time you plug in, then you have a spike, and it raises the power level. And so now, interesting thing about this is, okay, there are 2 humps of usage. So we have, for those 4 spots, you can see actually there are 6 different plug-in events for that particular day. And so people had to move, people had to cooperate, and so we've encouraged a community of users who then maximize the amount of usage that we can get, and try and keep those spots full so they don't get blocked by gasoline vehicles. So I've had a student take a year's worth of usage data from those 4 stations and then plot hour by hour what is the power level combined for those spots. And so obviously the first thing in the morning, nothing's happening, then people arrive at work, and eventually by 9 or 10 o'clock, we've got all 4 of those spaces actively used, charging to whoever has arrived. And now this is averaging over that year. This is a typical Monday. Now, because we have this group who are cooperative and do move their vehicles, then we actually have a second hump later in the day. It's not as sharp as the first one because there's a variation in when people are willing to move or able to move because of lunch and other schedules. But we're able to continue using the hardware and get twice as many users. And so essentially spread the cost and allow more people to charge with the limited amount of infrastructure. So this is a video camera view looking out over those same spots. And again, we can see how congested the parking lot is, and all 4 of the stations are in use. And, well, okay, so for some kinds of hardware, then you would authenticate. We don't actually have a requirement that you would swipe a card or put in any key code. And that's why, without any enforcement, then, you know, where there are cars that would park in the way. And so what we've been trying to do is figure out a way to monitor these spots and then provide potential users with information about whether the spots are available, and do that in a way that incorporates knowledge about cars that would be blocking but not plugged in. And so we have taken this video feed, and again, I have students processing the data, trying to figure out, can we identify different cars, or can we identify the situation whether the spots are full or empty? And I think I have, well, this is a little video clip. I don't think it's very high quality, but you can see once you zoom into the spot where those 4 parking places are, then throughout the day, I think this is, well, you can see some kind of activity. And by picking a particular zone of the picture and comparing image to image, then you can identify when has someone moved or when have they parked there. And that can be correlated with the power data from the e-gauge unit. So you could see a car arriving, and that's on a little loop, so it doesn't really show much. But you could correlate when does a car arrive, and then is there a power spike? Well, that must be an electric vehicle that just got here and plugged in. Or you could have a car arrive, and then there'd be no electrical activity, and it would be one of those bad gasoline cars in the way. And in either case, we can log that data and make it available through some kind of a cell phone app. And so I have a student who's been, well, I have some students who have been trying to incorporate the electrical data and the camera data to provide knowledge that would be in your hand with a cell phone app. And so potentially, and actually, some of the manufacturers of the EV charging hardware allow for different kinds of modes of reservations or how the billing is synchronized to whoever's using the spot. This provides a little bit more flexibility because it can incorporate in knowledge about when are the wrong cars in the way in a congested environment. So we're still working on this, and this sort of helps me promote the community of users and make sure we get the maximum use out of the limited infrastructure that we have. So next kind of case study is to think about fleet operations, and so it makes a lot of sense for a university or bigger organization to, the university owns lots of vehicles for maintenance, but right now we have this fleet of 3 Leafs. It's hard to say this, they're leased Leafs, but obviously most of the work on campus is a short drive, go and repair something, come back to the home base, plug back in, and so gathering data on those, well, at one level the data might be, well, how much energy are we using per month or year for how many miles? But I've installed the Fleet Karma is a company that puts or offers devices that plug into the onboard data port and can do speed logging, and you can have GPS, and then that data gets wirelessly transmitted to the cloud somewhere, and then we're able to log that. Fleet Karma interface gives data points on location, so we can track where the cars have gone, and we can track, and this map on the lower right shows the blue period is when did they charge, and then the green periods were times when the car was moving to repair something somewhere on campus. And so, again, well, this one didn't really need to be plugged in very much because of the short durations of the driving that happened to be needed for that car for that period of time. But here we have a trove of data. We can figure out, well, not just for those few days, but over a longer period of time, where are the typical places that we need to send for repairs? Where are, well, we plug in at certain places because we know we have chargers there. But in the future, when we're trying to supply or increase the fleet size, then where would be the best place to install them, to have them be most convenient to the places where those vehicles would need to go in regular operation. So, yeah, so those are a good source of data again, it's not a major decision, perhaps, where to install things, because often we have an office that's in a particular building, and we want them close, but it's a good data source. So we were able to emphasize this, the learning part. Then I had a senior capstone project, and actually we were trying to emulate the fleet camera and provide different kinds of faster GPS charging and correlate that with the solar array generation times. So this became a senior project, and so those are all now graduates. So let me go on to the last case study, which really was trying to use solar for transportation as much as possible. And so I've actually, it goes way back. I've been an advisor for solar collegiate racing teams, and so this is a car that we had built actually many years ago. But the way that the solar is installed, the solar feeds the grid. Electric vehicles, well, okay, a solar car doesn't need any kind of grid power, but all the other vehicles that we plug in get grid power, but they're really decoupled. We had solar panels on these cars for the collegiate, sort of squeeze as much energy out of that, or much mileage as you can. But this was never a car that we were going to be able to own, and it really, there's not enough square feet of area to put a reasonable sized solar panel to power things. But I did do the kind of calculation for a parking canopy solar array. Then you get more area than just the roof of the car. You get the entire parking space is essentially solar panels that are above your location. So if we were to think of that as a source of power for you as a plugging in at work, a workplace charging driver, if we decouple the solar from the car and we have it installed and it's always collecting when the sun is shining, and if we count that, then it turns out that for New Jersey and for typical commuting distances that we experience here, then a solar parking canopy is enough to provide the energy for a green commuter, if we were to attribute that. So decoupling is good. Now there's a whole bigger issue in terms of when you plug in, because when it's decoupled, then we really are thinking about the electric grid entirely. So this is a picture of our array. One of the factors when we have a parking canopy, because we build it to be sturdy and withstand windstorms, the steelwork supporting these is really monstrous, and so quite an additional cost compared to what you would pay for a solar array on a landfill or something like that. So studying how users plug in and noticing that for a commuter, a workplace charging commuter who would plug in from driving from home and then fill up in a relatively short period of time, then I started to wonder, well, how would that work? Would there have been some few different cars that have been offered with solar panels installed, not covering the entire roof area, but with some modest roof area? What would the energy consequences be for someone that had a solar panel on their car? And so if you had a solar panel on your car, this is a demonstration Ford model from a few years ago. I don't think you can buy those, but if you had solar panels in the roof, you think, okay, well, that's going to work all the time that I'm parked out in a parking lot anywhere where the sun is shining, like the solar parking canopy that you could park under. But if it's installed in your car, it ought to be collecting energy too. Well, So when you combine that, though, with the user behavior, if I have a car and I know that I've used some of the mileage, some of the battery capacity, and I get to work and there's workplace charging, I'm going to plug in if I can and have a full battery and be able to drive wherever I can. But as soon as we fill up the battery, then the consequence is that the solar panel gets turned off. Why? Well, the solar panel is trying to generate power and trying to put it in the battery, but if there's no space, then you have a congestion factor. And so it really depends on whether you have enough foresight to realize, okay, I'm not going to need all that range, and then leave some space in the battery to allow for sunlight to be captured. So most of us don't want to think about it. So we're not going to think about it. We're going to go ahead and plug in, and then solar panels might not have as much use as we might think they would. So for example, the black data points are essentially the sunlight intensity for a day chosen at random. And then it's imagining a scenario starting from home with a full battery. Well, it turns out, well, as soon as you start driving with a full battery, then it's not full anymore. And then the solar panel on the roof would be operational and collecting energy for the entire time that you're driving. So point A is when you hop in the car and start driving. Point B, you get to work, you plug it in, the battery's not full yet, but from time B to C, we're filling up the battery from the grid, and then after that point, there's a zone where it's parked there, plugged in, solar panels turned off, so you're essentially losing a major part of the potential solar. So you could counteract that. Actually, no. Sunlight varies everywhere because of weather patterns, because of geography. And so this is New Jersey kind of data. These are kilowatt hours per square meter. So that can be scaled to figure out what your car might be collecting if it had solar roof. And so the conundrum would be then, if we had a solar panel and we wanted to keep it working, then we want to make sure that the car was smart enough to save a little bit of battery space to always be able to accept the sunlight generated power. And so that requires that when you plug it in and it's controlling its charging on its own, it ought to be able to slow down and save a little bit of space at the top. But just the right amount of space, because we want to have as much driving range as possible. So it turns out we can do a correlation with the sunlight that's being delivered at the moment and make a prediction about how much sunlight we might be getting later in the day. We get a pretty good correlation. And we can use that to predict how much more sunlight from now will a car be able to get for the rest of the day parked in a parking lot. So thinking back to this scenario, we can reduce this problem by careful planning and build that into a smart system in the battery management system. Although still we can't buy very many cars with solar panels on the roof. Okay, so we need smart systems that take into account our user behaviors. When do we plug in? And then the technical side, how is the battery capacity? Is it full? Is it not? And how to synchronize those. Obviously, I'm a big fan of solar and expanding EV infrastructure so we don't have congestion problems like we have on campus. I hope that we'll be increasing our installations. But as we imagine more technical or more interesting scenarios for the grid, then we might want to have, when we have enough plug-in spots and we have enough cars with big batteries, then we should be looking at bidirectional power flow, a system called vehicle to grid that would allow us to shift power from different times of the day to offset peak demands when we're all turning on our air conditioning. And so actually the vehicle to grid scenario was pioneered by a professor at the University of Delaware named Willett Kempton. He's actually one of our speakers at the Rutgers Energy Institute Symposium on May 2nd. So I invite you to come to campus. We have a great panel covering battery technology, and then Willett Kempton will be speaking on V2G as well. So coming back to solar racing cars and solar panels on cars and technology, smart systems for managing those. Again, looking at what I do at the university in terms of educating students. Well, I don't have a car that has a built-in roof with a solar panel. So I bolted a solar panel into the Chevy Volt now. Now I do have a car with a solar panel on it. And so this is another student project where we're going to, well, the students are programming and building the electronics to measure how much solar we're generating throughout the day and be able to log that data. And so soon we'll be able to hire those students and when they graduate. Some of you I've talked to about my solar panel. It's not actually a very good idea to do this because of the wind resistance that you add. So this is a cosmetic and an educational project. But I get lots of people talking to me and saying, what is that? And so it enhances awareness. And maybe if we learn enough about how to manage the solar generated power and the battery capacity and plug-in, understanding the plug-in behavior of users, then maybe more car manufacturers will decide to be putting these into the contour of the right shape. I certainly would like to have a car that has that. Okay, so I guess this is my last slide. Thank you for learning more about the Rutgers ecosystem. And these are some of the names of students who have participated in projects like I've been showing you, so other things. Thank you.